Hi guys, I'm Wilson. Infrastructure team and compute group. So I will cover the first half, and then the rest of them will be covered by Varun. So let's start. First about the introduction, yeah. I just said we formed the Bytedance Infrastructure Lab, a compute group. So the infrastructure system lab, actually, we are focusing on the research in compute storage, database, and networking area. And in our compute group, actually, our research areas mainly focusing on the cloud native service, machine learning, and OS and virtualization. So we have several collaboration teams in Bytedance, and they are like the ByFast team, where they develop the fast system that using WebAssembly that can provide high density the WebAssembly instance deployment, and also a very short WebAssembly code start and startup time compared to Linux containers. And also we have RPC team that they actually working. They are actually maintaining our internal WebAssembly runtime, and which is currently based on WASM type. And they actually also implement the synchronous host call support in WebAssembly, in our internal WebAssembly runtime. And also for the client, actually for the client info team, they are working mainly on the client side. So they actually because on the client side the computing the power is limited, so that they use WebAssembly to to do some special effects like fireworks, so that so that it can show the better effects so that the performance can be better. And also they are developing downstream branch of QuickJS in our internal for our internal use that currently they are actually corresponding it to WebAssembly to run on top of WebAssembly. Well, if you move the run JavaScript runtime on top of WebAssembly, it might run a little bit slower. But I think but generally this is there are a need for this. So there are the scenarios we need to run QuickJS on top of WebAssembly. Okay, so now I will cover the WebAssembly microservices in our Bytedance. So here I will show the advantages using WebAssembly to run microservices. First, it's small, so if you compile your code, it will most of the time it will be a few megabyte size. And also you can do high density deployment, since the WebAssembly the code, when you compile them, they actually you can in the runtime you can actually compact several of them into the single runtime, so that you can have a more the WebAssembly instance running inside your runtime compared to Linux containers. And also, since it's small, it loading and starting it can be very fast. And the last thing is about the security. So it's secure and by design, and so that when you run it, you can avoid many of the problems that you have running. For example, if you have you using the V8 the engine to run JavaScript, and some it has you can actually there's some security issues, but using WebAssembly, actually many of the issues can be avoided. But there are limitations too. Later, so Varun will cover it at the end of the talk. And let's see the next one. So the architecture. This is the architecture of the or internal WebAssembly the microservice environment. So this is a fast system. So we have workers on each of the node. We have several workers running on each of the in each of the worker. We will have several WebAssembly instances running. So when the request comes, actually goes to the gateway, and it is dispatched to one of the workers and start the instance. And we have also we have agent running on each of the node. So what it does is whenever the request comes, if the WebAssembly instance is not it's not available, it's local, then the agent will help to download the artifacts. And also whenever there's new workers coming and then the agent will help to register the new worker to the management cluster. Okay, so the current status for the the fast system. So well, we was using WASM time because it's Rust based and using the Rust language. I mean, you can avoid a lot of simple mistakes that you use for example in other languages like C or C++. But at the same time, we're actually evaluating using WASM Edge. The reason that the more features are supported from WASM Edge, and actually, for example, using Dapper or other some for example, more support for the Linux socket. So I mean, probably later we will switch. We will be able to switch between WASM time and the WASM Edge depending on the user need. And also the languages support in or the fast the microservices. So they are first JavaScript supported, Rust supported, and C++ supported. And for the Go, we're actually using TinyGo to compile the or Go code, but it's a little bit different. There are a lot of features it's not as the same as the Go, but to run in WebAssembly, I think TinyGo it's you can be used, and actually they are actively developing, improving the TinyGo, so there are more features probably will be supported in the future. For example, the better code routine and also better garbage collection. For the here probably I can talk a little bit more about the JavaScript running environment. So we were using SpiderMonkey JavaScript the engine and compile it to WebAssembly, but later we realized that there are many issues with it. First, the code base is not updated very frequently, and also there are many issues using it. We see different kind of crashing issues. Then later we decided to also support QuickJS, and then the client infra team that I discussed in the very beginning actually helped to make the QuickJS support here, so that the QuickJS is much smaller, and although compared to the performance, it's a little bit slower than SpiderMonkey, but QuickJS generally the code base is very small. It is manageable, and if we want to have new feature, it will be easier to add. And here I mentioned the wider. What the wider does is that when you bring up the JavaScript, it needs to initialize itself. But what a wider does that when you use a wider, you actually can pre-initialize the WebAssembly module and run some initialization functions, especially here in this case JavaScript, so that we initialize the environment. Later when we load the code, it can be faster. And here, the three frameworks that we ported to WebAssembly, internally in Bytedance, we have our RPC framework and also HTTP frameworks. So that these are the two frameworks we're using internally. And I think it's also available on GitHub. But this is the framework we use a lot in our internal microservices. But when we when we are making more microservices in WebAssembly, then we need to port these two frameworks to WebAssembly. Now this I think is still in progress, but many features already supported. So in the near future, we are going to move more or internal microservices probably to WebAssembly. Okay, and here I will talk about the challenges and solutions that we see on when we are doing all this kind of the stuff. So first thing about the artifact size, this is particularly for WASM time, but it can also be true for other runtimes. So what we see that when you compile your WebAssembly code, later you can get it has different sections. After that, for example, after you compile your WebAssembly code, then you can pre-compile it to ahead of time to native code. So after that, later you can load it. It can be loaded and run much faster. But when you pre-compile them ahead of time, then it will generate several sections. And one of the sections actually contains the debug information. So actually the size is pretty huge. So it can take around like 1/3 of the total artifact size. For example, we have like 26 or 27 megabytes of the code after pre-compiled, and later after we remove the section, then it will be only like 16 megabytes. So we reduce a lot of unused data, because this debug information might be needed in when we are actually debugging it, but when it is coming to the product environment, then we don't need this information anymore. And then this is something that we discovered. So basically, for your code, there are also you need to take a close look and see what you really need, and then you probably can remove some of the information so that it can help you to run your load your code faster. Okay, so the second thing is about the combined deployment. For the WebAssembly, actually, we can run several functions, inside one worker, so that they are running in the same memory space. Actually, when they communicate with each other, we don't need someone else from outside to get involved. So in the originally, when we call function A to function B, we actually, even if the function B is scheduled on the same node in the same worker, but we still need to forward the function the request to the gateway, and then the gateway will forward this request to the function B. But later, we realized that we can do better on this part to speed up the communication. Then what we did is that the agent, locally, we will decide. The agent will help to decide if we need to run the function, can bring up the function locally. Then what we will do is that if we can bring up the function, like the destination function in the same worker, then what we will do, we will not let the gateway getting involved. Well, we will just forward the request from function A directly to function B, which is brought up in the same worker. But here I probably did some error in this graph, because here actually the communication should be directly from function A to function B. The agent here probably it will just get involved with some lookup, some simple lookup, which is just for example what's the metadata of the function B. But actually the actual request will go directly from function A to function B. Okay. So now my colleague Varun will cover the rest of the talk.
Hi. So in production, we have a Bytefast system, which is similar to AWS Lambda. So Bytefast is function as a service, and at a time we can be easily running thousands to tens of thousands of functions at a given time. So at that time, debuggability in production becomes very important for us. So this is like a small system that we built to easily debug or profile an ongoing function. So there are two key parts here. First part is WebAssembly, we are using WASM time as one of the flavor for the WebAssembly engine, and it does not provide a good debuggability feature right now. So one issue is this dotted line is one WASM time, runtime, and we have multiple WebAssembly modules running. But if I try to, so they are within one engine, we have multiple WASM time modules running. But if I try to profile one function, it will by default right now profile all the functions. And if on one node I have, let's say, hundreds of functions running, I don't want to profile everything because it reduces the performance. So we have to build around some system so that for the function for which I want to profile, we start a new engine. So an engine is basically the sandbox environment, like the isolation between the WebAssembly runtime. And we only run that one particular function right now. And first is profiling the function, so collecting the GIT dump. And second is to integrate with our ByteDog platform. So this is the generic platform which takes like the GIT dump and the profiling information for all the languages, for all the tools. and it provides a nice output like this. So this is something like how we have a Grafana dashboard. So any user can submit a function request that, okay, I want to profile it, and underneath we will manage everything. We will notify the ByteDoc profiler to collect the information, and the user can directly see it on the dashboard. So this is one thing that we built. Second is on the shared memory. So whenever we have like microservices or functions, when they are communicating with each other, what is a typical RPC workflow is, first the service A or function A will serialize the data. Then that data will be copied from the user space to kernel space. When it is copying, there is an interrupt and context switch from the kernel space. It will be like via NIC driver, it will be wired to another node. There also, again, it will go to the copy to the kernel space of the receiver, then interrupt, context switch, again back to the user space of microservice B and deserialize it. So this adds an overhead, and with functions which will be typically running for few milliseconds, we want to reduce that overhead. So for that, WASM time recently added shared memory. So with shared memory, all, and now that Wilson talked about the function chaining, like the combined deployment, when they are on the same node, it makes it simple that we do all the operations in the shared memory, like in the user space, so we can minimize the serialization, deserialization, number of times we have to do it, as well as we don't have to depend on the kernel space, no interrupt, context switch. So we are right now like doing the POC on like evaluating the shared memory, doing the performance benchmarking, how better it is compared to doing the RPC call. So in the POC phase right now, we are evaluating between two functions directly using like one shared memory. Eventually, we want to look into the global pool so that we don't have to garbage collect once the functions exit. So the goal here is to improve the function performance as we go into like more functions, have a that kind of like how microservices communicate with multiple microservices, we increase the function complexity. Lastly, this is the last slide. I will discuss about some current limitations that we are seeing in the production space on moving on onboarding more applications towards WebAssembly. So first is lack of features. So right now we don't have garbage collection like Go routines for Go language. Right now, open source so if I basically it's like compilation part. So if I take a lot of open source packages, if they are like I think Michael also mentioned like 70% support is there, like 70 or 60% of libraries can be compiled. But yeah, like the more complex packages like for Golang, Net HTTP, they will have pretty much dependency on other 100 packages. So it won't compile or it will have difficulties. Then lower level OS features, for example, with respect to networking. So WASM Edge has a good support. WASM Time recently added some socket support, but it's still not to the mark. Debuggability we talked about, so we'll have to still there like memory profiling is not there. If I want to do live debugging, that's missing. GPU support, as well as within a WebAssembly runtime between multiple functions, we don't have like the C group kind of resource limitation. So there is a FASM, which is open source. Like, yeah, it's open source. They wrote a paper. They added the support for that. So hopefully other WASM time and WASM Edge pick it up. The performance cap is right now, we noticed that we tried to compile some microservices and the Kitex framework that Bytedance open source. When we compare the performance with respect to the native runtime language, there is 20% or so, like in the good case, 10 to 20%, in some cases, even like 44-50% performance degradation because they are not written with WebAssembly as a runtime. They are more targeted towards their own native runtime. And with interpreted languages like JavaScript, the performance hit is even bigger. So yeah, these are some limitations. Lastly, yeah, we are hiring. So, yeah, thank you.